Radiocarbon is produced in the upper atmosphere, and this occurs when the cosmic rays, mainly from the sun, enter the Earth's atmosphere, and they, through a series of what we call spallation reactions, produce neutrons. And it's these neutrons react with nitrogen-14 to make carbon-14. Okay? Then that carbon-14 is rapidly oxidized into CO2, and then it can be introduced into the food chain via photosynthesis of plants, and then we eat the plants. So if you measure the radiocarbon content of something in our bodies that turns over very rapidly, say our red blood cells, we would have about the same carbon-14 to carbon-12 ratio as the carbon-14 to carbon-12 ratio in the atmosphere. But when we die, that carbon-14, we'll start to see the decay of that carbon-14. Okay, so radiocarbon or carbon-14 decays via a process called beta decay into nitrogen-14. Beta decay is the emission of an electron, and you can understand this process if you think that a neutron, which is neutral, is made of one positive proton and one negative electron. So if one of the 8 neutrons in carbon-14 emits an electron, we're left with a proton. So we've now increased the number of protons to 7, and we've decreased the number of neutrons to 7. So we've changed the element into nitrogen, and it's got a mass of 14. All radioactive isotopes decay in a similar way. So we have what's called an exponential decay curve, and those decay curves are defined by their half-life. So radiocarbon has a half-life of about 5,730 years. So after just under 6,000 years, we'll only have 50% of the carbon-14 atoms in a sample left. And after just under 12,000 years, we'll have just 25% of those carbon-14 atoms left. And by the time we get to 50,000 years, there's so few carbon-14 atoms left that we can no longer measure the 5 or 6 atoms that might be left. If we know the starting concentration or the starting ratio of carbon-14 to carbon-12, and we know the half-life, we can work out, or we should be able to work out, the radiocarbon age. The difficulty with radiocarbon is that we don't actually know that starting concentration of carbon-14 to carbon-12, or that starting ratio, because this has changed in the past. Okay, radioactive decay curves make an excellent, what we call chronological clock, because they're not affected by heat or by chemical reactions. So we can heat a bone or we can heat a piece of wood to make charcoal, and it's not going to affect that rate of radioactive decay.